In this lesson, we're going to make consumers that are redundant. That is, if one consumer fails, another consumer will be available to process messages off of the Kafka topic. There are a few different ways to do this. Let's draw one method, which would be to have two consumers, one running hot and one running cold. So here we have the broker, and here we have the hot consumer. So it will always be pulling messages from the broker. Then, let's say we have the cold consumer right here. It doesn't do anything. It just sits there waiting. In this kind of setup, you need to have a communication channel open between the two consumers so that if the hot consumer fails, the cold consumer knows to pick it up. So if this one fails, the cold consumer will come in and start processing messages off the topic. Now another way to run this would be to have two consumers running hot. That means that both consumers will be pulling messages from the broker and processing them. So we have the two consumers here pulling messages from the broker. Now there are two ways to do this. The first would be to have all the messages go into a single partition. We'll say into partition 0. And both consumers are subscribed to partition 0 and pulling messages. And what that means is that they're both going to get exact copies of all the data. So the consumers will need another component that will enable them to communicate between each other so that they know which one has processed which messages. Now you can use Zookeeper for this, but our examples will use Redis. The second method for having two consumers run hot is to publish messages to two partitions and have the consumers read messages from those partitions. So we have the broker, and we have messages coming in for partition 0. We have messages coming in for partition 1. Now, let's look at what the consumers will be doing. So if we have two consumers, they'll be pulling messages from either 0 or 1. The difference is only one consumer can be pulling messages from one partition at a time. So say this consumer is pulling messages from partition 0. If this consumer wants to pull messages, it can only pull messages from partition 1. However, they use a polling mechanism to pull messages from the broker. So, if they pull a set of messages on partition 0, they can switch over to another partition at any time. So these consumers will actually loop through the partitions and at any time be pulling from either 0 or 1. They'll use Redis to coordinate who is reading from which partition at which time. All right, let's get into the code and implement one of these. I've created a producer already that will write messages to a topic BigData HA that we can test with. Here's the code of that producer. Now we're going to tackle the first example, which is producers writing to a single partition and two consumers running hot, reading from that partition. So here we see we're going to publish 10,000 messages to partition 0. We're just going to set the ID as the iteration and some message. Now it's important to note in this scheme, if you're going to have messages that need to be processed only once, and the consumers are going to coordinate who is processing which message, you need to have an identifier that uniquely identifies each message coming through the system. That way, when a consumer starts processing it, it can tell the others, hey, I've got this message and I'm taking care of it. So let's look at the consumer. I've started us off with the basic framework: Ruby gems, Kafka, Redis, and JSON. We make the Redis connection, we make the Kafka connection, and we're reading off of partition 0. All right, let's get the consumer started. The first thing we're going to want to do is define a group name for the set of consumers. So if we have two consumers that are reading off of BigData HA, we want them to be defined in a group, because they could be making copies for their own thing, whereas there could be another process that's pulling data off the topic, and they'll want to be their own group. So you have separate redundant groups running at the same time. So the consumer group name will be BigData HA. Now, we're also going to keep a queue in Redis of IDs of messages that we're processing. So we're going to name that BigData HA processing. And then we'll have another queue in Redis that specifies which messages we've actually processed. It's good to have two separate queues for processing and done. That way, if one consumer picks up a message and starts processing it and exits before it finishes, the other consumer can pick it up because it will see that the message isn't in the done queue. All right, data HA done. Now, let's have the consumer go in a loop to process messages from partition 0. All right, we're reading messages in. Let's parse it out so we can actually get at the message ID to figure out whether or not it's something that we should be processing, or if the other consumer is taking care of it. So let's talk about what we're going to have to do to have the two consumers coordinate with each other. We're going to use the scripting feature in Redis, which will allow us to update values in Redis and take action depending on what those values are. So we can send a script to Redis that says, if this message is in a processing state, don't do anything. Or if this message is in a done state, don't do anything. Or even better, if the message hasn't been seen yet, set it to a processing state and return back. Redis is single-threaded, so it will guarantee that only one consumer will be able to put a lock on that message at a time. So we'll write a script in a little bit that will tell us whether or not a message is in a process, done, or waiting to be processed state. So here's the call we'll make to Redis, where we run the script and determine what state it's in. And we'll have to pass it keys, which is an array of arguments that the Redis script will be able to access. We'll pass it the two queue names so they'll know where to look to determine whether or not this message should be processed. And we'll also pass it the current time and the ID of the message. All right, let's put a little output here to see what that state is, so that when we run this later, we'll know which consumer is taking care of which message. Okay. Now we decide whether or not we want to process the message or wait for later. So when we write this process message script later, we'll have it return process if the consumer should process it. That is, the message isn't being worked on, so it should be done now. So here's the stage at which we'll do stuff with the message. And then we can mark it as done. So marking it as done will require the writing of another script that we'll send to Redis, and we'll call that one the mark done script. And we'll pass it arguments. Again, the keys, which will be the done queue name and the processing queue name, and the arguments, which will be the time and the ID of the message. Now the next case is that the other consumer has picked up the message and has started processing it. So the return value for that will be processing. So if that's happening, what we'll want to do is we'll want to put the message somewhere and check back to see if it's done processing. So if a consumer picks up a message and it starts to process and it fails, in a few seconds when this consumer polls the server again, it'll see that it still hasn't completed, and then it can actually process the message itself. Finally, there's the last possibility, which is that the message has already been processed and we don't have to worry about it. So let's look at what these scripts are that we're going to be sending to Redis. They're a little lengthy, so I'll copy and paste them in. All right, here's the process message script that we're going to be sending to Redis. This is a Lua script, so it's a little bit different. We're going to define a variable called isDone, and we're going to set it to the value of a sorted set. We're going to look at the first key, which was our done queue, and we're going to send it the second argument, which is the ID of the message. If it's not done, then we know it's either in a processing state or it hasn't been processed yet. So let's check to see if it's in a processing state by checking the other queue, the processing queue, and again sending the ID. If it's not processing, then we know we want to process it. So we'll write into the processing queue here and tell it the time that we started processing and the ID. That'll allow us to see later on how long something has been processing for. And it'll also allow us to clear out the processing cache. Finally, we'll return process to tell the Ruby script to go ahead and do something with the message. Now, if it was processing, then we'll return that so that the consumer knows to keep the message and check again later to see whether or not it should start processing it. Finally, the last case, which is the message has already been done and we can ignore it. Now let's look at the mark done script. This one's pretty simple. The first thing we're going to do is we're going to add this message ID to the done queue. So again, the done queue was the first key that we passed in, the time was the first argument, and the message ID was the second argument. So in that case, we know exactly what time a message was processed. And then we'll remove that key from the processing queue. So that should keep the processing queue smaller and more manageable. And we'll also tell the other consumers that try to pick up off of it that they shouldn't hold the message for possible processing later. The last thing we'll want to do in this consumer is we'll want to clear out the processing cache periodically. So one way to do that is to just keep track of how many messages we processed. And then, say every 1,000 or 10,000 messages, we'll try and clear out the cache. So we'll clear it out every 1,000. And again, we'll use the Redis scripting functionality to call a script called trim cache. Now the only queue we need to trim is the done queue, because we were clearing out the processing queue as messages were completed. Here we see we're going to keep the size of the done queue down to 1,000. We could have it be much bigger. Now let's take a look at the trim cache script. So first, we passed in what we wanted the max cache size to be. We'll check to see how big the done queue is through this method zcard. If the cache size is bigger than the max cache size that we want, which was 1,000, then we're going to trim it. So first, we have to figure out how much we want to pull out of it, and then we call the zRemoveRange command to the done queue and trim there. With the high availability consumer written, let's run it and see what happens. All right. Let's run the producer and see if the consumers pick up different messages. And we can see through the output that some of the messages are processing, and some of them have already been processed, and some need to be processed. So this technique uses quite a bit of horsepower on the side of Redis, but in addition to making it highly available, it actually allows you to scale consumers operating on a single partition. Next, we'll look at a technique for having two consumers reading off of multiple partitions. It's much easier to work with in Redis, and it's a little bit less code. Okay, let's write the producer for that first. We can update the previously created producer to work with this new technique of publishing messages to two partitions. We'll just do the same thing we did in a previous lesson, where we randomly selected which partition to send to. So ideally, messages will go in between partitions 0 and 1. Now, let's write a consumer that can pull off of those partitions. I've started us off with the usual things: Ruby gems, Kafka, Redis, and a connection to the consumer. In addition to the normal arguments, I've also specified a max size. And here I'm saying 100,000 bytes. I'll get to why that's important in a little bit. As before, we're going to give ourselves a consumer group name. This will uniquely identify our two consumers that are running together. BigData HA2. We're going to have two partitions that we're splitting the data between. And now we'll just loop continuously to read off of them. So what we'll do is we'll look at each partition in turn to see whether or not we should be processing on it. So 2 times we're going to loop through, and we're going to say look first at partition 0 and then at partition 1. How this will work is that each consumer can only be pulling messages from one partition at a time. Also, each partition can only have a single consumer processing it. That means when a consumer is processing messages for a partition, it has a lock on that partition. We'll use Redis again as the locking mechanism for this. So let's define a key that we'll use in Redis as our lock. This is where the consumer group name becomes important. Because we have BigData HA2, that means this group of consumers, between them, one of them will have a lock on this partition. So if we have a totally separate group of consumers that want to consume data off of this topic, they can do that and have their own locks. All right, now we'll check Redis to see if the partition is currently being processed by another consumer. So the command we're using here is setNX, which has a return value that depends on whether or not this key, that is the partition processing lock key, has been set before. So we'll check the return value to see whether or not it's a partition that we should be processing. So if isProcessing is equal to 1, we know that we just set the key for the first time, so we should be processing it. The consumers are responsible for storing the offset for where they were last processing messages in each partition. We use Redis to store where the offset is, so that the two consumers will be able to coordinate with each other. So the key name we'll give this, we'll again use consumer group name and the partition to namespace it. We'll also want to make sure that the lock that we acquired through the NX command expires so that if this consumer dies, the other consumer will be able to pick it up. Now, you may want to set this to happen in a Redis script or in a pipelined command. That way, you can ensure that if the consumer dies after it's acquired the lock, but before it's set the expiration, it won't be locked forever. Lock key, and we'll set it to expire in 2 seconds. So the consumer will have 2 seconds to do its work. Now let's look at what the last offset was. Okay, so we're getting the last offset key, and that could return nil if it's the very first time. So let's make sure to set it to 0 if it hasn't been set. Finally, let's make sure that's an integer. Okay, so with the lock acquired and the offset set, let's pull messages off the queue. All right, this is the point at which you'd want to do your processing. Once you've done that, you'll want to go ahead and remove the lock so that any consumer is then free to pick up the partition later. And we'll set the last offset while we're at it, so that the next consumer will know where to pick up from. And we clear the lock. And then we're done. And that's this entire method. As you can see, it's a lot simpler and a lot less code than the previous one. However, this method isn't as scalable as the other one, in the sense that if we're only running 2 partitions, only 2 consumers can be processing at a time. So as the number of messages you publish to a topic goes up, you'll have to add more partitions. However, that could adversely affect the performance of your Kafka cluster. In this lesson, we've learned how to write a high availability consumer using 2 different methods. One acquires locks for processing specific messages between consumers, all pulling from a single partition. The other one has the 2 consumers shifting between the 2 partitions and acquiring a lock for the partition as a whole to do their processing.